Okay, so we'll make a start. We'll make a start on this final session this afternoon. So I'm Chelsea from UQ, so I'll be chairing the final two sessions of the day. So our first speaker this afternoon is Professor Dana Kulic from Monash University, Professor of Robotics. So she'll be speaking about learning to engage machine learning for interactive architecture.
Thank you very much for the introduction. Is my mic on? Yeah, okay, perfect. Thank you very much, Chelsea, for the introduction, and thank you all very much for being here. It's really exciting and energizing to be here at Grace Hopper and with you all. As Chelsea mentioned, I'm a professor in robotics, so I'm not an artist or an architect. And the work that I want to tell you about today is a really exciting and fun collaboration that I have been engaged with a group of artists and architects, where we've kind of developing and integrating machine learning methods into architectural and artistic systems. I recently arrived at Monash University, but this work was done while I was at the University of Waterloo and while I was part of the Living Architecture Systems Group. So what is living architecture? So this is a concept that was initiated by Philip Beasley. He's a well-known artist and architect based in Canada. And his objective is to design architectural scale systems that can be perceived as near living or living things. So what these systems do is they have sensors so that they can sense the presence of occupants and visitors in the space, and they also have actuators so that they can respond to those visitors. So what does that look like? So here is an example of kind of a zoomed in view of that system that I showed in the earlier slide, where we can see there are shape memory alloys which are moving those fronds, and then lights that can be turned on and off, and then also sound that can be made. So when I first looked at one of these systems, I thought, okay, there's a bunch of sensors, there's a bunch of actuators, and somebody has to figure out how to map from the sensors to the actuators. So this is just like a giant robot. I don't know if Philip would be happy to characterize one of his systems as a robot. But one of the central challenges that the designers of these systems face is how to make this mapping between the sensors and the actuators. So the system perceives that there are visitors in the space and that they're moving in the space. How should it respond? And traditionally, these interaction behaviors are basically designed by the architect or by the designer. So they have some creative idea, this would look cool, this would be really exciting, and that's what they implement. So one challenge with this, when you have a designer designing these behaviors, then the design is usually done once at the start of the exhibit, and then it remains constant for the duration of the exhibit. But this can kind of be, especially if you have a long-term engagement, then you can initially the interaction is very magical, but then you kind of figure out the trick and then it loses its magic. So what we were interested in is, would it be possible to design interactive behaviors that are continuously evolving and changing so that we can support kind of like a longer term interaction? And would it be possible to generate these behaviors autonomously? So rather than having the designer designing these things, can we have an algorithm that could be doing that kind of design? And then finally, what kind of behaviors best engage the viewer? So what kind of thing, how can we actually figure out, what kind of behaviors are interesting, and then use that to help our autonomous design process? So we actually started to kind of answer these questions initially with a master's project that was with my student Matthew Chan. And we thought about, okay, so we want behaviors that would change over time. And we want this kind of autonomous generation of behaviors. So, and also, we want behaviors that are not just reactive. So not just a person does A, they move in the space, and then the system responds. We want it to move to kind of a shared initiative system so that both the interaction can be initiated by the visitor, but also the interaction might be initiated by the system. So we were thinking about, okay, well, what would motivate an artificial agent to do something? And we were very inspired by the work in machine learning that was looking at curiosity as a motivator for acting, and especially curiosity as a motivator for trying new things. So we basically kind of conceptualized this, our interactive system, as an autonomous agent that had a notion of curiosity, and this curiosity would cause it to generate novel behaviors. So the idea, so how do we conceptualize curiosity computationally? Basically, we're looking for things that are new and unexpected. So we think about the possible actions we can take, we make a prediction, and then we see what actually happened. So if our prediction is absolutely correct, then this behavior is not so curious because we know exactly what's going to happen. But if our prediction is not correct, then potentially this behavior is curious. But we want more than that. We want something that where behavior that we don't know about, we can't predict well, but our prediction is improving, so that there is the potential of learning. And we hypothesized that this might result in some kind of lifelike exploration. So we started very small. We set this up in a small test bed where we built this kind of small-scale interactive system where we had 4 nodes, and each node consisted of some moving parts, the tentacles, and also some sensors. So we had accelerometers that could sense the movement of the fronds, and also IR proximity sensors that could sense the proximity of visitors. And here's our first demonstration of this learning system. So you can see here the system initially starts learning. And what it's doing is it's basically trying out actions and then trying to predict what will be the consequence of that action. And so initially you can see it like it lit up because it was trying to figure things out, but very quickly it learns, okay, when I turn on this light, I perceive this light sensor. When I move this frond, I can see the change in the accelerometer. But you can learn, this is basically just its own behavior. It learns pretty quickly. But now a person enters the scene, and now these expectations are violated. So all of a sudden, now the system starts generating actions again because it's trying to figure out what's the mapping between my actions and the responses. And you can see here, the system actually generated response. It appeared to be in reaction to the human visitor, but in fact, this was not pre-programmed at all. It was just based on this notion of curiosity in the system. So this was kind of just like a first demonstration. So then we thought, okay, well, what about visitors? Would this kind of learning system actually be interesting to visitors? Would they even notice that this was happening? And would certain behaviors be more interesting than others? So we ran a very small user study where we invited people to come into the studio and interact with the test bed. And then what we did is we had, for the first 10 minutes of their interaction, the system was basically running prescripted behaviors, so this was designed by the designer. And then in the next 10 minutes, the system would start running the learning algorithm. And we wanted to see, would people notice that there was a difference? And would they prefer one or the other? And we found that the response was mixed. So some people found the prescripted behaviors boring, and they actually thought it was quite interesting when the system started doing things that was unexpected. But other people kind of found the learning system quite frustrating because they were like, I don't know quite what it's doing, and I think it starts doing one thing and then it switches to something else. And they actually didn't find it engaging. They actually found it quite frustrating. So there is kind of this interplay between, the curiosity level of the visitor and the curiosity level of the autonomous system. The other limitation of this study is that this was kind of quite contrived and artificial, right? So we kind of recruited participants, we brought them into our test bed, and then we had them filling out questionnaires. So it didn't really replicate the true experience that people would have interacting with such a system in a more realistic setting. So in the next phase of the research, we really wanted to think about these questions more thoroughly. So really, how can we actually maximize visitor engagement and interest? And in order to answer that question, we first needed to figure out, well, how do we know that the visitors are engaged and interested without asking them to fill out questionnaires, which is quite disruptive to the experience, to the interaction experience. And then we really wanted to move beyond this kind of artificial HRI study and really move into, okay, can this work in an actual museum setting? And so this was work that was done by two of my students, Lingheng Meng and Daiwei Lin. So to answer this first question, we actually wanted to reformulate our learning so that we actually explicitly try to maximize the visitor engagement. Of course, one possibility for maximizing engagement is to have a human designer who thinks about, okay, what would be the most engaging to the visitors and design those behaviors. And we use that as our baseline. Our alternative approach is to actually try to learn the best policy, the best interaction strategy online during interaction. And so we wanted to use something like a reinforcement learning framework, which is kind of a very common technique in robotics and other AI agents. So the idea behind reinforcement learning is that you formulate some kind of reward function, and then you interact with the environment to try to figure out the best policy, the best strategy to maximize that reward. And reinforcement learning has been incredibly successful over the last few years. So if you think of the examples of the machines that have beat champions of chess and champions of Go, all of these machines use reinforcement learning. But the challenge is that these machines take millions and millions of experiences to come up with the best policy. But in our case, we want the system to learn during interaction with people. And so we can't really have the situation where the system tries out millions and millions of really uninteresting and boring actions. And then, after several years, finally it does something good, and the person is like, okay, now you've got it. We really want the learning to be happening much, much faster than that. And so in order to enable this fast learning, we need a good low-dimensional representation. So what we thought is, could we actually exploit the designer specification as a starting point for learning? So unlike typical reinforcement learning algorithms, where we start from kind of knowing nothing, we actually use the designer specification as the starting point. And we use two parts of the designer specification. The first is actually, what are the behaviors that might be potentially interesting? So we use the specification from the designer, and then we basically parameterize those behaviors and learn in the parameter space rather than learning in the raw actuator space. And then we also use the initial conditions. So basically, the initial parameters at the start of learning are the ones that were specified by the human designer. Now, in order to make this work, the other thing that we need is we need to formulate the reward, right? So we need to be able to tell the system when it's doing good, when it's maximizing engagement. So of course we can ask people in questionnaires, are you engaged? But I think that's quite disruptive. You're trying to experience this artwork, and I'm coming by with a questionnaire and asking, how do you like this? What about this? And also it's not scalable if we want to go to kind of hundreds or thousands of people. So what we thought to do instead is to use the existing system sensors to estimate group engagement. So what we want is to basically, without people being aware of it, to estimate how engaged they are. And the first type of engagement is just being there. So if you're in the space and you're not leaving, presumably, it's at least a little bit interesting. But then we also want to know if you're really interested and if you're actively interacting with the system, that's probably an indication of an even higher level of engagement. And the third thing that we really wanted is for this to work in crowded and uncontrolled settings. So in a real museum and not just in the lab. And so we, together with Philip, we convinced a museum where Philip had an exhibit to let us basically test this out. So this is the Royal Ontario Museum in Toronto, and this is opening night of the exhibit. So you can see kind of, tons of people. We don't know who they are. We haven't recruited them. They've just showed up. They want to check out this interesting artwork. They don't know anything about, machine learning or human-robot interaction. So how do we actually? So there's a whole number of challenges, technical challenges, to get this to work in this kind of setting. So I want to quickly highlight some of those. So here is kind of a graphical overview of the system. So there is a number of nodes, and each node consists of a shape memory alloy. So this is the part that allows the system to move. And then there is also some LEDs for lights. And then we also have IR sensors that sense the proximity of the participants. And then there's also a little vibration motor so that the system, the other type of actuation is kind of this shaking movement. So this is our hardware. So you can see the sensors here are the IR sensors that can sense the proximity, and then the actuators are the lights, the sounds, and the vibration. We also had 2 cameras in the system, but we didn't use these for learners. This was just to allow us to kind of observe the space. So what we wanted to do is we wanted to estimate our engagement based only on the IR sensing. And so what we looked at is what's the distance between the IR sensors and anything in the scene. And so if the distance was less than maximum, but still fairly large, this is basically passive interaction. So the person is just kind of standing there, below the sculpture, but not interactive. And then if we had very short distance, it meant that people were actually reaching out their hands to touch the system or to wave at it. The other challenge that we had is kind of unlike a lot of lab settings, we weren't free to come, if the system breaks down, we can't just kind of show up and start repairing and debugging. So everything had to be running, in the museum setting all the time. And the only time that we could make changes is either very early in the morning or late at night. So we had to be able to figure out, so that's actually one of the reasons why we had those cameras, is because we had to kind of establish a remote operating center. So if anything went wrong, we could remotely log in and kind of do remote repairs. So it's quite an engineering challenge of getting this to work. So here's a video of, this is kind of like a late night debugging session when we're kind of making sure everything's working. You can see the security guard walking by in the corner over there. And this is kind of like the only time that we had, after the system was set up and running, only late at night could we actually come in and make any kind of code modifications. So what we convinced the museum to do is to let us remotely log into the installation and then every few hours change the operational setting. So we had the system sometimes running in pre-scripted mode. So this was basically just using the designer settings. And then we would switch it to learning mode. And we had 2 types of learning mode. The first learning mode is where we were just learning from scratch. So this kind of standard reinforcement learning setup. And the second learning mode was when we were learning, but also exploiting, leveraging the designer's expertise. So I want to show you, before I show you the quantitative results, I want to show you kind of some of the kind of examples of interactions that we see. So one thing that we learned very quickly is that the type of interaction you get is very much determined by the context. So what's happening in the group? Who are the people there? So you can see this initial video. There's a gentleman who is walking around. He seems interested, but he doesn't actually know that it's possible to reach out and and interact with the hand. And then in the second video, the woman comes in and she reaches her hand, and now all of a sudden he realizes, oh, you can reach your hand up and it'll do something additional, and now the entire interaction changes. In this video here, you can see that we have been we're being visited by a school group. And the type of interaction that you observe when you have a school group is very, very different than the type of interaction when you have just, 2 adults. And I'm not sure why this last video is not playing. Let me see if I can get it going again. There we go. So in this last video, we are actually demonstrating, even though that we started from behaviors that were designed by the designer, we actually end up getting behaviors by just playing around with the parameters that are quite different than what the designer initially anticipated. You get these big kind of bursts of kind of like thundering through the system that people found quite interesting, but is not something that the designers originally anticipated. The designers typically, their prescripted behaviors were more looking at kind of more slow pace rippling. So even though the system was learning based on kind of the designer specification, it was able to generate some kind of quite novel and interesting behaviors. So what about the quantitative results? So we had this measure of active interactions, and we wanted to see kind of what happened as a result of learning. So if we look at over the times that we ran the human design behavior system, the system that was learning with no human input, they achieved kind of a similar number of average number of active interactions per hour or per minute. But when we combined the human designed and the learning systems, we got significantly more active interaction. So people seem to be engaging and interacting with the system much more when it was generating these learned behaviors, leveraging on the human designer's expertise. And then we also, for a subset of the people, after they left the exhibit, we approached them and asked them if they would be willing to answer a questionnaire. And we used the standard Godspeed questionnaire, which asks about, so this is a standard human-robot interaction questionnaire that asks about how do you perceive the machine in terms of anthropomorphism, animacy, likability, perceived intelligence, and perceived safety. And what we found is that between the two systems, basically all of the perceptions were quite similar, but people tended to like the learning system quite a bit more. And the key part was here the interactivity. So the interactivity was rated to be significantly higher for the learning system. So the key findings is that we found that the best interactions occurred when we combined human expertise with autonomous learning. But actually what was most interesting is the learning system, it's not because, the improved performance was not because the learning system found some best optimal policy, which is typically what we find in reinforcement learning. Actually, the improvement was because the learning system was continuing to adapt. So it was coming up with a different policy depending on who was in the room. Whereas using simply the human design systems, the design was always the same for any kind of interaction. And so what we saw is when we had a big boisterous crowd, the system learned to do different things than when there was a lone visitor. So what do we want to do next? So I showed you earlier in the slides that we had looked at this kind of idea of curiosity, which is a type of intrinsic motivation. And then here we used kind of an explicit reward structure, which is extrinsic motivation. We are interested to see whether we can combine these two to generate kind of more interesting long-term behaviors. The other really promising direction is when we shared these results with the designers, and especially the videos of the behaviors, they were quite excited because they were like, oh, that's a really cool behavior. And they wanted to then take that behavior that was learned and tweak it because they were kind of, oh, that's a good idea, and what about doing this? And so really kind of thinking about not just taking from the designer kind of at a single stage and then just going forward with it, but actually kind of bringing it back to the designer and saying, okay, here's what we found, and giving that to them as an inspiration for designing even cooler and more interesting behaviors. And then the other thing is, in this system, we started to measure engagement using these proximity sensors, but this is, of course, just a very rough approximation. So we're very interested to think about what are other ways that we could measure engagement that would be transparent to the visitor and allow them to really enjoy the interaction without realizing that they're being, that the system is measuring the engagement. So I want to end by thanking all of my students, Lingheng Daiwei, Matthew, Mo, and Ali, and thanking Philip, Rob, Adam, and the entire Philip Beasley architectural team, and especially the Royal Ontario Museum for taking this risk and letting us run this really fun experiment. So thank you very much for your attention, and I'm happy to take questions.
I think we have maybe time for one short question, or else if you've got any. One short for you?
But you said that you would change between having it on the designer setting and then having it learn. Would it just like continually build on that learning, or did you reset the learning every time?
So we tried with both, so we ran the experiment over 3 weeks. And we had to restart this, of course, with any kind of engineering system. We had to occasionally restart the system. We had one unfortunate incident when our entire system went down and all the learning was lost. So our initial intent was to continue learning, but we actually did, because of these technical issues, we had to restart the learning multiple times. So actually, yes, having the benefit of prior experience does help. But actually, even from a restart, it was, the learning was fast enough that even within a single session, so each of the sessions lasted about an hour. Even within a single session, we could see significant improvement.
Okay, that's great. So really interesting talk in a really interesting area. So I think we're out of time for this session, but if you've got any questions, perhaps you can catch up in the break. And our next session is in here at 5:05. So I look forward to seeing you all then. Thank you.
Great, thank you.
Okay, so we'll make a start on our last session today. So welcome back, everyone, to our last session of the day. So we'll make a start. So our last talk today is from Habiba, a research engineer at CSIRO Data 61, and she'll be talking about deep learning on graphs.
Hi, everyone. Thanks so much for making it to the last session. So yeah, I'm Habiba. I'm a research engineer at the Research and Design group in Data 61, and I particularly work with investigative analytics. And what we do there is deep learning on graphs. So it's deep learning and specifically for graph kind of data. So why are graphs even interesting? It's just that, implicitly and explicitly, graphs are part of our life. All our social networks are graphs. Transport networks are graph. Our academic citation networks are graphs. So they are so ubiquitous that we usually don't even notice that they're everywhere. And deep learning in of itself has just started cracking down on work in incorporating data that is interactive, that is connected. And this is what we do at Data 61, and trying to build a whole platform where we can use approaches for data which is connected. So what kind of problems that are there that we can solve using deep learning on graphs? There are pretty much every problem boils down to one of the three things. One of the most popular thing is node classification or node inference, which is something like this, that if, for example, you have a network like this where you have a set of individuals about whom you know the political affiliation of some of the individuals, but not of the other. And what you want a machine to be able to predict is the affiliation of the unknowns. This would be a node classification, standard node classification problem. And here, looking at it, what you can see is that we have a set of individuals that have some kind of interaction among them, which is represented by these edges between them. And what deep learning on graphs is supposed to do is leverage that extra information about who is interacting with whom, in addition to what an individual features or properties are, what seems to be an individualistic choices that somebody's making, and what are the choices their friends are making, to be able to infer what would be their, say, political affiliation. The second kind of problems that are of interest is link prediction, which is again that we know that certain individuals are connected, but what we want to know is whether those that are not connected should be connected or can be connected. And one of the standard applications that you can see is in LinkedIn when it's suggesting you people that you should connect to. What it does is that it looks at your professional profile, what your interests are, who you are connected with, and then try to suggest you people accordingly. So this would be a standard link prediction problem. And the third problem that is something which we encounter very, very commonly is that we try, given any kind of a social network, what we want to know is compartmentalize individuals in different groups, however we define the groups that, So this would be a standard problem that, you have a set of individuals, you would have a set of individuals, and what you are interested in is that what kind of groupings that these individuals are associated with. And so now let's step back and see that how is this different from standard machine learning. I mean, this was something that has been done in machine learning forever. These are the 3 standard ways machine learning can help solve different problems. But then what is the value addition a graph can provide for these kind of problems? So for that, I'll use this Twitter example, a more realistic kind of example. And this study is about classifying hateful user on Twitter. And by hateful, all that it means is that people on Twitter, when they're tweeting, they tweet their opinions, which could be sometimes divisive, sometimes that could be problematic, whatever your definition of being a problematic opinion is. And other times it could be just any nicer ones. So the first, once you actually even sign up on Twitter, it usually have all these policies and terms of use, which states that what kind of content you shouldn't be talking about and so on. But and somehow they also do some kind of machine learning to be able to detect that if some user is talking about something which it doesn't agree with their user agreement and would either block the account, cancel it, and whatnot. So now, given this kind of data, the question is, and given that we have information about a certain subset of individuals who are, let's say, have a more negative way of talking, and then some there who are not, or let's call them other, can we predict that? What would be how would we label the rest of the individuals? This data set is available at Kaggle, and it's really interesting one to experiment with. And the original work was done back in 2018. And it's a user study of about more than 100,000 users. And out of them, 5,000 are annotated as hateful and normal, and that is actually hand annotated data. So basically, the tweet of about 5,000 users are analyzed to determine whether this user overall is hateful or not, right? I mean, it's not as if like individuals come with a label, but it's just that based on what they are tweeting or talking about, they are labeled. Now, what needs to be appreciated that it's just that like going through tweets after tweets of about 5,000 individuals is really an uphill task, and it's a data of more than 100,000 individuals, and it's just a sample of Twitter, right? And there are about 95,000 which are not even labeled. So the question is, can we actually determine what would be the, how would we label the rest of them? And this would be a standard machine learning question. The way these researchers have done it is using hand engineering these set of features based on user tweets and activities, and then using that as a starting point for the machine learning approach. So the way it would work is that you have some hand labeled data about users who are hateful and non-hateful. You have a whole set of features about all the users. You feed it to a trainable machine learning model, and it returns you the prediction for the unknown cases. And since it's a probabilistic model, it will sometimes be right and sometimes it will be wrong. But yeah, that would be the standard way it would be able to do the prediction. Now, what could a graph structure help here or improve the process? So the fact is that in Twitter, it's clearly people retweet other people's tweets, and the fact is that it results in a network information. So now what we can add to the just a standard machine learning model is this interactive behavior, that it's not just this individual who is writing about something, but it's just that who are the people that it is retweeting, and so we know that they are mutually influential to each other, and that could help us to better determine, in a more precise way, determine what would be their affiliation. So that's how graph machine learning would differ from a standard machine learning approach. So what is the core of any deep learning model in graphs? It's basically the graph convolutional operator that has been extended from a standard convolutional operator to graph kind of data. When you have unstructured information, that you have interactive information, how would you actually use that information to build a better model? An extension or improvement or a more scalable version of it is when you are not looking at the entire graph, but you're somehow subsampling it, and it's called, in general, it's called graph sage. Now, what do these models do in very abstract words? So what it do is that you train a model using the graph structure, which is represented by some kind of adjacency matrix, which is like one-to-one interactions of all the entities in a given network. You feed the model the node features, so basically the individual features, which is what the standard machine learning would do. So the things that is different is this structure information that goes into the model. The model has these trainable weights, which it learns over many iterations, and then you apply some kind of sigmoid function, which is just to squish your values between a certain range. This is just for mathematical tractability. Doesn't matter for now, but something that you need to do so that once you have many layers, it's just a single layer. But when you have many layers, you can have values which could be infinitesimally small or very large, and you just want to be able to contain them within a certain range. And then it outputs you something which could be like a prediction in case of node classification, or link prediction in case of links when you want to determine links. So this could be your output. So yeah, this is how any standard graph machine learning approach would work. This is the core of it. What the Graph Sages does is that it improves on this approach in a way that it makes it more scalable. So what happens here is with this aid that you need to have, if you want to predict political affiliation of one individual, you need to know the entire graph structure to be able to do that, which could be highly infeasible for a very large network. So for the Twitter example, there was just a small subsample of Twitter, 100,000 user. It's like a 100,000 by 100,000 matrix that you're feeding into it. And so one can imagine that computationally it's very expensive. But on the other hand, it's not very useful as well. So if, for example, if you want to label me, it's just that at most my friends would be a good indicator of who I am or how I should be labeled, or maybe friends of my friends, or maybe friends of my friends of my friends, if you just want to stretch it even further. But realistically, you don't need to look at the entire social network to be able to determine anything about myself, right? So this pretty much is trying to come up with a precise answer based on everything, which is not really helpful. So this is where the graph sage is helpful when you're actually just sampling the graph. You look at just a subset of neighbors or neighbors of neighbors, and that's how you would go about like how complex you want to make the model. And the deeper you go, the less precise it will be, or depending on what kind of application it is. So this, for example, is a one-hop neighbor. When you're looking at just one-hop neighborhood, what you're doing is that you're aggregating. You sample for a given node Ni. You would sample some subset of its neighbors, not the entire set, but just fix something. So it's a tunable hyperparameter. You would look at you would pick up some neighbors. You would look at all the features, or however you define that the neighbors are, and you would aggregate that information. You would you would concatenate the features of that particular node you're interested in with the features of its neighbor, and you would again have some kind of trainable parameters that are fed into the model will train on. apply the same, some kind of nonlinearity function like sigmoid, ReLU, etc., and get an output. So what happens is, so this is pretty much what graph machine learning is. You start with some kind of convolutional operator, and then you sort of try to improve upon it, that how much you want to, how much information from a network you want to look at, how much you want to sample, subsample, how you would do that. Graph Sage, how many times you would subsample a network so that you have a more robust solution. And yeah, that's pretty much how you would build it. And this is what we actually do in StellaGraph, which is an open source Python library that we are building in the investigative analytics team. It's built on TensorFlow, Keras, and NetworkX, and it's open source, so you can go to the GitHub repo and download it and start playing with it. It has a whole bunch of demos, which walks you through all the different approaches that we have. It's really we try to make it as simple as possible so that, given whatever your data is, whatever your question is, you should be able to easily load that data, be able to train a model and visualize the output, and iterate over this process. So also we are very we love to listen from people who are interested in problems with graph machine learning. So so if you have a problem you're interested in, but you don't know what you should be doing with that, you just send a message, and somebody would answer you, and we are genuinely curious as to how people actually can use graph machine learning on any kind of real application. So I cannot stress this enough. So always feel free to shoot out a question, and somebody will answer you. So what does this library has in itself incorporated? We have a whole bunch of methods for link prediction and node classification, two of the problems I mentioned earlier. So anything from GCNs, GAT, graph attention networks, to Graph Sage, and versions of it are already implemented. Moreover, we also for the unsupervised settings, so we have graph embeddings and unsupervised methods. So unsupervised methods are when you actually don't have even those partial labels, so those had annotated labels for the Twitter data. What if you don't even have that much information? So what can you do? So we have approaches for that. One of the biggest, I think, differentiating factor is the interpretability. The problem with most of the deep learning methods is that they are complex and they're really hard to explain. So even if you have built a model which is very accurate, gives you 80, 85, 90% of accuracy on your particular data set, you probably need to play with a whole bunch of hyperparameters to be able to get to that point. But then once you get a new set of data, it may not work exactly as good as on the data that you trained on. And the big challenge is that because of the complexity, because of all the weights that it's parameter that it's training on, it becomes very hard to explain it. So what we strive to do is that to bring in this interpretability, that once you have built a model, we should be able to explain a way that what is it paying attention to, what are the how is it building these weights. So for example, if there are certain features that stand out as opposed to something else, so how do we actually find out that what's important? So as an example, I'm working with Transport for New South Wales, and we are trying to build a model which can predict speeds on Sydney road networks. And the thing is that even if we come up with a good prediction model, what we need to know is that what are the problem junctions, where are the points which needs to be paid more attention to. So what if if an incident happened, an accident or some construction is happening, and the people are not using the road system the same way as usual, what is the things to pay attention to? And interpretability becomes important when it's a real application which has lots of stake at the end. So for that, this is really important for anyone to be using the system to be able to understand what is the system actually doing in the end. Another important part is the probabilistic methods. Most machine learning is all about probabilities, and what it'll give you is an answer which will have, will tell you that, yeah, it's an 80% chance that this user is a hateful user or not. What happens is that maybe if you retrain the model, the probability may not be the same. So it's not really, because it's not very stable. What you need is some kind of confidence. So for a particular user, if your model is telling you that, yeah, it's a hateful user or not hateful user, what you need to know, the extra information that would be super helpful would be that how confident that model is about its judgment. Say, for example, a user tweeted only once in 5 years, and your model is going to tell you one way or the other if it's a hateful user or not, right? But one tweet is not really a good way to judge someone. So maybe, if your model can give you this sort of extra information that, yes, I'm telling you that based on that one single tweet or however tweets that user did, this is what I think he is or he or she is, but my confidence in that is not really high. So that when you're making a decision, you actually have something else extra to go with. Also, so far I haven't, what I had completely not mentioned is that graphs are not necessarily very so straightforward that your social behavior. We are not like one-dimensional people that we just have friends, or we interact in so many different ways and so with so many different groups. So which results in this in networks that are more complex. We have different kind of relationship, not just one kind of relationship. So heterogeneous graphs are those in which we are incorporating these multiplicity of relationship which are qualitatively different, and what can you do about it, and which is actually a very interesting problem in of itself. What we are currently working on are the temporal and dynamic graphs. So again, graphs are like the Twitter example that I gave was just one snapshot of Twitter. Twitter after that, that was from data was from back from 2018. Since then, everyone realistically Twitter would have changed so much. People would have tweeted and retweeted so many new things. So it's just that what it's telling me about this snapshot of data from 2018 is not really necessarily applicable to what is happening today. So real world is dynamic, it's changing. So what happens when you have these networks that are evolving over time? How do you actually do machine learning on graphs that are changing? So yeah, this is something we are trying to tackle, and hopefully we'll be able to crack this problem as well, and we'll have new approaches implemented in our library. So yeah, that's it from me. Other than, so if you need to know more about Stellargraph, my colleague Tan will be talking tomorrow about scalable machine learning using Spark. So that's another whole side of machine learning where you are actually dealing with really big data. Most of these problems are really are interesting when you have a manageable kind of data set. But what if but in reality, none of the data that we see is simple or small. So what happens when you are trying to do machine learning on scale, and how you can, what kind of problems and challenges you face and how you can solve them. So yeah, Tan will be talking about that. Yeah, that's it. Thank you.
Really interesting talk. We've got some time for a few questions. Are there any questions? Yeah.
So what's the scale properties that algorithm can?
So usually within like 10,000 of nodes, features, nodes, and like thousands of features, you would be easily able to do all the approaches within on a single machine. Yeah. But anything bigger, you would need to do something on a distributed system, and that would require that your algorithms are able to do this graph convolution in a distributed environment, which is, with all the message passing, it could become complicated for different reasons. So yeah.
So does CBLA support that, or?
It does. We are trying to extend it to a scalable version. So for certain approaches, we are going by from method to method, and yeah, the long-term plan is that it should be able to provide scalable methods for pretty much any data. Right.
Any other questions? Yeah.
Yes.
Thank you. I did miss a bit of your talk. I was really keen, but I couldn't. I was caught up with something else. So my question is about the data sets that you mentioned out in the real world that are changing, dynamic, and they're really big. They have a lot of information. What if they hold all those properties, but they're also sparse in nature? how would we deal with big data sets that are quite sparse, and how would you address such an environment, such a use case scenario through this paradigm?
So one way to deal with it would be sampling. That you would need to incorporate, you would need to look at subsamples of the data and try to train the model based on the subsamples. Once you have trained the model, you have trained your weights on this on the sample data. You could do anything like node classification, prediction on the larger data set on the trained weights. That would be one way of doing it.
Yeah. One more final question.
Sorry, it's like to run around.
How do you deal with something like intentionality or someone whose behavior changes over time? So maybe they were hateful when they started using Twitter, but they changed their mind and then they're proactive.
Yeah.
Are we anticipating that kind of behavior at all?
So this is great question. This is what the temporal and the dynamic graph scenario comes in. So temporal is when you feel like your network is not changing, but their properties are changing. So that could be that their behaviors are changing. You can think of it as anything from stock prices fluctuation. So again, things are changing, but and how are they affecting the prediction overall? So this is what we are trying to do. That bring together the LSTMs as well as GCN. So how do you look at the structure and incorporate it into the temporal information and have a end-to-end training model that is able to learn from history and yeah, give you precise answer in whatever point of time you're looking at. Yeah.
Okay, so I think that's all the time we have for questions. If you've got any more, perhaps you can catch up in the reception and networking next.
Sure.
So that is the end of our first day. Thank you all for coming. I believe. Thank you for the introduction. So I believe there's the reception and posters and networking is out on the Plaza Terrace.